On video now, so it's be hard. All right. Oh,
Dan Erickson's going to draw
that
it.
again. All right.
Tony missing
Red today.
Yes, you did.
Black is pretty good.
We miss you so much, Dan. I wish you were here.
Chris, you know that goes to Ava.
Is the sign somewhere?
I don't care. It also goes to Dan.
I'll try.
Unless they put a sign.
Unless it goes on YouTube.
I know.
Yeah, it should be on there.
Okay, so today we're talking about, we talked about metals last time. Today we're going to talk about ceramics.
Sorry, he said the board is really messy on computers.
I can't do anything about it. And we have the, I'm guessing this is some kind of cleaner.
Probably, because it says cleaner.
There we have one nice spot on the board.
How much does that bother you, Joyce?
All right.
Bother you
Okay,
that much?
so today we're talking about ceramics. And the next time we'll talk about processing both ceramics and metal.
Customs?
I wanted to mess with that, but I came in too early, and now I just kind of have nothing to do.
Ceramics and glasses. Hey,
What?
Yes, those
Okay.
are glasses.
ceramics and glasses. In general, these are a combination, as we talked earlier, of a metal plus carbon, nitrogen, oxygen, phosphorus, silicon. Mostly, that covers most of the ground. So they're chemical compositions, they're ionically bonded, we talked about that earlier semester. There are two broad categories. The largest category are oxide ceramics. So we have Al2O3, alumina. Anybody know what alumina is used for? Nobody has any idea.
Railings.
Try again. SiO2, silica. Anybody know what silica is used for?
To in new shoes.
What?
In new shoes. They put the silica in the new shoes, the little packets of silica,
Oh, yeah,
shoe
right.
boxes.
Okay.
Thank you.
Alumina, silica. Silica is sand, right? So it's a glasses and windows are made of silica, silicon dioxide. It's the primary ingredient in most windows. It's in crystalline form. It's quartz. In a crystalline form, aluminum oxide. I can't remember how to spell sapphire. I don't know if that's right. Sapphire is aluminum oxide, two B's. That's what this didn't make sense, but okay.
Sap.
Sapphire. Okay, so sapphire is made from aluminum oxide. Garnet made from aluminum oxide. They're aluminum oxide with different impurities. That's where the color comes from, the impurities. Aluminum oxide itself is clear. Industrial applications of aluminum oxide are for polishing. So it's an abrasive compound used in polishing. It's fairly hard. What's that? Sandpaper. So garnet sandpaper. Exactly. Okay. Magnesium oxide. That's a refractory metal or refractory ceramic, being used in high temperature applications. Zirconia, ZrO2. That's a structural material. It's actually a very strong ceramic. Another example, barium titanate. It's for nonlinear optics. Okay, so I'm just throwing up some examples. This is by no means exhaustive or even the most popular or anything like that. Well, silica is probably the most sand all over the place, okay? But those are the oxides are the most commonly formed ceramics. But there are some that are non-oxides.
So the two types are oxides and non-oxides.
Right. Kind of narrows it down. Oxides get their own category because there's so many of them. Silicon carbide, also used for abrasives, for sandpaper. So you get silicon carbide. Tungsten carbide. Tungsten carbide is oftentimes used as a tool for tooling. It's a very hard material. Silicon nitride, or boron nitride. These are used in high temperature applications, structural applications. Silicon nitrides are used oftentimes in high temperature bearings. So the balls, instead of being made of steel, because steel can deform at high temperatures, the balls have been made of silicon nitride instead. So they can operate very jet engines and that kind of thing. So those are the two. So these are all, and all of the examples here I've given are of the crystalline form of those ceramics. And so quartz, yeah, because your window's not made of quartz, right? This is not crystalline. It's an amorphous material.
If we break it, will it be crystalline?
Nope. The non-crystalline form we generally refer to as glasses. So these are, if you talk about ceramics and glasses as two different categories, oftentimes the crystalline form is called a ceramic, the non-crystalline form is called a glass. But there's not necessarily that doesn't always hold. And glasses are then amorphous. They have no crystal structure. They're basically like frozen fluids. So they have the structure of the fluid, but they're locked in place. So they're homogeneous, isotropic, all those sorts of things. Okay. So those are the two broad categories: ceramics and glasses, crystalline and non-crystalline. The properties of ceramics that are most of greatest interest to us. I've got, how many do I have here? 1, 2. Yeah, okay. Really only have 2 categories. The first is mechanical properties. What is the biggest distinction that we've already talked about for the mechanical properties of a ceramic? Brittle. Right? The biggest distinction is that they undergo brittle fracture. Right? So if we pull them in tension, there's basically no give to them at all. Right? There's very little. Remember, when I drew it, I drew like a little bit of a plasticity at the top. The reality is, on the scale of the diagram, remember I was exaggerating the scale in that drawing. In a real scale, they're basically just linear up to the point of fracture. So on that scale, well, here, this is in tension. In compression, they more like behave like this. More likely to behave like this. Or the tension numbers like down here. So a glass or a ceramic material has a much greater strength in compression. Why is that?
Because the inside is already under compression.
No, cracks.
So,
Right? Because it's cracks that, if I'm pulling an object in tension, then cracks in the surface are going to open up, and I'm going to create stress concentrations that weaken the material substantially. But in compression, those stress concentrations don't exist. I'm not pulling the crack apart, I'm squeezing it closed, and so it has a much greater strength. Yes?
Are there like any materials that really act opposite of that?
that have much stronger properties in tension and lousy in compression.
Or is it pretty much standard for materials?
I mean, metals are pretty much symmetrical. Ductile materials are generally symmetrical. They have the same properties of compression and tension. There might be something like a non-Newtonian fluid, for instance.
Silicone?
So that's what I just said, yeah. Non-Newtonian fluid or silicone.
We should play with somebody for class one day.
No. So unless you can bring in a gallon. If you bring in a gallon of silly putty, we'll play with silly putty in class. It has to be a gallon. How much does it cost to buy a gallon of silly putty? You will find it to be expensive. Anyway, okay, so I can't think of anything else. Okay.
Dude.
So, oh shoot, this was actually supposed to go first. Sorry, didn't mean to jump into mechanical properties just yet. Sorry, let me go back. Let me go back. That now? That enough?
I just came here for coding.
Sure. It's sweet of you. Anyway. You should come back when we're actually doing electrical properties.
That actually went better than I was expecting.
I got my head back today.
Brought it on yourself. Okay, sorry, let me go back to the glasses over here. Talk about some specific kinds of glasses. Okay, I've got 4 different specific types of glasses. Vitreous silica. So, vitreous silica is pure SiO2. No dopants, no additives, pure SiO2. As such, it has a high melting temperature. And so it can be used for furnace windows, for instance. Okay. But it's uncommon. Most of the glass, that you see around you is not pure silicon. Sounds really loud, whatever that is. Soda lime silica. So soda lime silica has on the order of 15% soda. So sodium oxide. On the order of 10%, oops. Calcium oxide. And then the remaining part, 70% or so, SiO2. So that's what your common glass windows, drinking glasses, that kind of thing, are made of soda lime glass.
Is that just because it's cheaper?
Well, it's also much lower melting temperature, so it's a lot easier to work on. Okay. Next is E-glass. Which is, getting down to the bottom of the board here, but on the order of 55% silica. 22% soda, 15% alumina, and on the order of 8% borate, B2O3. So when you make a fiberglass, right, you guys have heard of fiberglass? Right, it has glass fibers in it. Hence the name. So E-glass would be a candidate for fibers in fiberglass.
Why is it called E-glass?
I honestly don't know.
Is it flexible enough or?
I assume, I could guess, but it would just be a guess, that it has to do with the fact that they're trying for something with a good modulus. But I don't know.
So it's not one or more of these things, it's like plus.
Right, that's the total composition. Nominally. They don't all add up, but
Yeah.
close, okay. So, excuse me. This is by far the thing you're going to encounter the most. Soda lime glass. And there will be different compositions of soda lime glass. When I get to I'll talk about the optical properties. I don't know if I've got a full chart or not. And I don't. I don't know if they've got a full chart in here either. That doesn't look like it. No, they don't. Anybody who takes my optics class will actually cover in greater detail some of the distinctions from these various different classes, and the different refractive index and dispersion characteristics and so on. And then the last type of glass is the glass that's used in optical fibers. Here, these are proprietary compositions, so they're not, there's not like a single thing. But there's most often still at least SiO2 based. So the plurality of the composition is silver. And many of them have fluorine added.
Fluorine?
Fluorine, F.
Fluorine.
Many of them have fluorine added to reduce the attenuation losses.
So this would be used in fiber optic cables?
Right. Because a fiber optic cable's got to go a long distance, and so you don't want to have any attenuation. You don't want it to block out any light. You want the light to go through.
So what property of this makes it so that it can be strung into a cable? Because you bend those cables.
Right. So it's just you make them thin. Okay. So if you do the mechanical analysis, the thinner it is, the less stressed you get on the outer edge. Because if you think about it, if I take a beam that's this thick and bend it, there's a big tension on the top and a big compression on the bottom. Because it has to do with the relative, the center line here doesn't have any tension in it or compression. And the further you are away from the center line, the more tension you have. Does that make sense? So if I make a really thin fiber, then I'm not going to ever be very far away from the center line. And so I'm not going to have nearly as much tension on the surface as I would with a thick fiber. So most of the ability to bend a glass fiber is just the fact that it's thin.
So, but you could bend it enough to shatter it?
Yeah, you can snap it.
Can you do that with, like, the soda lime silica glass? Could you make it thin enough?
Sure, yeah. I mean, I don't know if you've ever worked with microscope cover slips. Right, the little, those are generic soda lime glass, you can bend them. Okay, now you can't bend them, in a radius this big, but you can bend them without breaking them. But the other thing is optical fibers typically very polished. So the number of cracks on the surface are going to be significantly reduced so that you give them even greater strength. Right? If I can polish, the difference between a regular piece of glass in tension and a polished piece of glass in tension is substantial. It's still the same line. But you get further up, if you polish it, then you've got fewer cracks to initiate a failure, a premature failure. So those are the two things. And then they also sheath them. Okay, so they're inside of another material, so that even if the crack tries to open up, there's something else there to keep it closed. Yeah.
How would you make something like that? Because on like a regular wire, you draw it through dye or whatever. But
Right.
with
glass, you couldn't do that.
Yeah, so we'll talk about that with when we get to processing, I think Wednesday.
To get a gallon of silly putty, it would be about $130, $140.
Okay. Thank you for
Do
reporting.
they
that.
sell it in those amounts?
No, you have to buy like
Just a
100
crap ton.
eggs. Yeah.
Okay, so depends on how much you really want to put so they can take class.
Can we make it if we make
No,
it as a count?
no,
Why don't
no,
you just
no,
make
no.
it, dye it red, and bring it to class? Say you bought it.
Okay, glass, so this is, so we've covered glasses and ceramics. And there's a third category that kind of is a mixture of those two that are called glass ceramics. The most common of these is lithium, Al2O3, SiO2. It's a combination of those three oxides.
What's the dot?
Just the indicating that it's a stoichiometric combination of those three.
So it'd be like a plus.
No, because it's all one chunk.
The stoichiometry.
Whatever.
Plus.
He's too far away.
It's not, the point is, it's not a chemical, this is not a composition, right? This is not a single molecule. It's a physical mixture of this and this and this.
I mean, you didn't have to get rid of them, I didn't mean to make
Make
you self-conscious
Anyway.
about that.
So in other words, the idea is it's not Li2, Al2, SiO6. It is these three things in combination.
Yeah.
Okay. And what happens here with the stuff is I guess the process is it's formed as a glass. So in other words, you take an amorphous version of this and you form it to the shape you want it to be in as a glass. As you blow it, you know, like a glass blower or whatever, into the glass shape. Then you heat treat, oh man. You heat treat it to induce crystallization. So we've got this glass, it's amorphous, we've probably had some kind of rapid cool at some point to allow it to stay amorphous at room temperature. But then we heat it up once it's in its shape and allow it enough time at that high temperature to crystallize, because the crystalline form is the preferred form. That's the equilibrium form.
Isn't glass stronger though?
Isn't glass stronger? No, typically the crystals are stronger than glass. Quartz is stronger than the glass window,
But you just can't see through it.
but it's not hard. You can't form it. You know, you can make quartz windows, but it's very expensive to make a quartz window. You can still see through it.
So how, like when you kind of cross-hatch grain boundaries, that prevents cracks from propagating? If
Yes,
it's just a
this
mess.
is brittle, so there's no crack propagating. There's no dislocations propagating anywhere, right? It's brittle material, so there's no ductility to worry about. So the crystalline material is actually softer. I'm sorry, harder than the softer glass. Okay.
Great.
And typically you get more than 90% crystallization. So basically what you end up with, if you look at the microstructure, is you end up with crystals, right, with this gooey, glassy area in between them.
So how do you make like wine glasses? Like all the crystal glasses, is that what that is?
So no, this is like Corningware,
Pyrex.
not Pyrex, Corningware. I don't know Pyrex. I don't know if Pyrex is actually
Is it the same kind of thing?
crystalline or not.
Extra
Could
strong
be.
glass?
Yeah, but it could be Pyrex is also crystalline, but I know Corningware is crystalline. Okay, but again, the point is, it's stuff that has a very low coefficient of thermal expansion. Right,
So
that's
the
why
other
those-
kind, is that just ceramic?
The other kind of what?
Like, you say like you have a crystal glass for like your tableware or whatever?
Oh, like lead crystal, like that kind of thing, like.
Right.
So,
Lead crystal?
what's that?
Say lead crystal?
Yeah, lead's one of the doping elements in crystal, in some crystal. It gives it a very high refractive index, high clarity. I'm not sure exactly what the value of the lead is, but anyway. So, no, those are not necessarily crystal in this sense. Okay. What's this? What?
To have lead in your glassware, wouldn't that be dangerous?
It's locked up in structure. It's okay.
Okay.
Anyway, and the way that you induce the crystallization is you dope it with just a little bit of impurity. So you use, crystallization occurs at the impurities. So you can imagine you have this big thing of glass, and you sprinkle a very fine powder of titanium dioxide, which is the same stuff that makes white paint white. Sprinkle it in there. So there's very little of it in terms of the actual composition, but it's enough to serve as a local nucleation site. Again, I'll refer back to the heating the cup in the microwave. Right? You got to get things to nucleate. You got to get to grow. So if you don't have the titanium in there, then it's going to stay as a glass. It's going to be hard to get it to start crystallization. But because you put these little bits of titanium in the mix, those are sites where there's a disruption in the lattice, and we'll try to begin crystallizing there, and then form the structure of crystals separated by boundaries of glass at the interface, at the grain boundary interface. This stuff is fine grained. Typically on the order of a micron or less. So, micron is it's submicroscopic almost. The reason it ends up having such better mechanical properties is that there are no pores. Like the grain boundary areas, which if we took a crystalline material and tried to make it into a shape as a crystalline material, we'd have to basically compact the crystal together at high temperature and pressure in order to get it to form together into a solid chunk. And inevitably in doing so, we're going to have porosity at the grain boundaries because we're never going to get them to squish together and fill in all the spaces. However, if we start out with something that's amorphous to begin with, it's a liquid, essentially, and so it's able to flow into, fill all the spaces, and then I grow grains from within it so that there's no porosity in the material. As we've said before, the porosity, which is what acts as a crack, a place for a ceramic or brittle material to break. Okay, so by doing it in this order, we actually make sure that there's no porosity and therefore much higher strength. Now fine grained, no, well, I guess that's number 4. No pores, so higher strength. And then finally, low coefficient of thermal expansion. So that's why your Corningware is able to go from refrigerator to oven to tabletop.
Is that CTE or is that supposed to be?
Coefficient of thermal expansion, CTE. I think I talked about that earlier in the semester. Yeah.
Can you drill holes in that stuff?
Probably when it's glass. You wouldn't want to do it when it's crystalline already, I don't think.
What would happen?
Well, you said you don't want to initiate defects, right? So you'd like to drill them out so that they can be, so that whatever defects you generate in the process of drilling it go away. So you can form the holes basically as a glass. That's the way you'd want to do it. if I drill it, I gotta have a diamond scratching on this thing to go through, and so if I drill a hole, I'm gonna leave defects, you know, cracks in the surface that I don't want there, it's gonna weaken the material.
You could heat treat it after you drill it, right? To reflow.
To reflow it, yeah, but only if it's glass. Once it's ceramic, it's not gonna reflow properly. Any other questions?
Corningware is all white because of the titanium? Or the,
I don't know if that's the case. I don't know if that's it. It could, the main thing is probably just the grain boundaries. You have different grains of material. If you, you may have different index of refraction, and maybe the titanium, but I assume that it's probably white because of the grain boundaries. You don't know what to say?
He's actually on the corner.
I'm just looking, I'm trying to find some spots.
Why is Corningware white? Yeah. I'm guessing it's probably because if I have light going from one crystal to the next crystal to the next crystal to the next crystal, and crystals, as we'll talk about in just a second, don't have a uniform refractive index in all directions. They're anisotropic, so that the light scatters around, it bends. Every time it goes through a new crystal, it bends to a different angle. And so that the process of doing that causes the light over many small grains to randomize and scatter in multiple directions. That's why I'm guessing that's why it's white. I doubt that it's related to the titanium. Okay. Any questions on the mechanical properties? Then we shall talk about the optical properties.
So this whole glass ceramic section is with mechanical properties.
No. Well, I was talking about primarily about mechanical properties and yet glass ceramics, but
Okay.
it's their mechanical properties that are the reason that they're used.
Okay.
Right?
They're not like the subheader mechanical properties.
Now, that's what I said. I meant to hold off on the mechanical properties until after I talked about the three forms: ceramics, glasses, and glass ceramics.
So now-
Okay. Optical properties. So by and large, most optical devices are made from either a glass/ceramic or a polymer. And those are the two broad categories of materials that are that can be transparent. And so the transparency makes them useful for optical properties. Generally speaking, if it's a cheap product, it might be made of plastic, of polymer. If it's a higher quality piece, then it's probably not made of polymer, but made of ceramic or glass. Okay. Those are the optical properties that are particularly interesting. So let's go through several. Everybody remembers refractive index from UFIS? Snell's law? Somebody can tell me Snell's law?
Is that the angle
Cosine angle instance times n equals, or n1 equals cosine angle.
Nope.
N2 over N1 equals sine of theta 2 over sine of theta 1.
Okay, that's correct, although it's generally more generally written as N1 sine theta 1 is equal to N2 sine theta 2.
Just choose the wrong.
Cosine theta sine, yes. Okay. So N is the refractive index, that's how we typically use it. Do you know how the refractive index is defined?
Something based off the speed, I think. The speed of light, right?
Yes, it does have to do with the speed of light.
The speed of how fast light travels.
With her, is it the
It's
speed,
the
like,
speed of light divided by its velocity.
Right, so speed of light divided by the velocity in the medium. So what is the refractive index of a vacuum? 1. What is the refractive index of air? 1.00029 is the refractive index of air. So it's not 1, but at 4 sig figs, it's 1. Okay, so, and if we demonstrate Snell's law like this, it's like this. This is n greater than 1, this is n equal to 1, roughly. Right, so you have theta 1, and this is theta 2. All angles defined with respect to 1. Okay, so that's why that's one of the ways in which we use the transparency of the material to change the direction light goes through. Then, so light is constrained. And there's a lot of other stuff, total internal reflection, all that kind of stuff, that drives fiber optics. We were talking about the fiber optics earlier. There's a lot of things that are based on this. Yeah, I'll come back if I have time to talk about maybe some of them. But this is the key property. And different materials have different velocities and therefore different refractive indices. The refractive index of glass, or of SiO2, is on the order of 1.45 to 1.65, probably on the high end, depending on how you dope it. Right, pure SiO2 is more on the lines of 1.45, but you can add dopants, add some boron, some phosphorus, whatever, all those things I mentioned at the beginning, and you can tweak the index of refraction up. Okay? I'm going to say this, but I don't remember for sure that I'm right. Diamond is on the order of 2.4, I think. The refractive index. I'm sure somebody could look that up. Aluminum, I think it's on the order of 1.8-ish.
Yeah, diamond, right, 2.419.
Okay. And aluminum should be just a little bit below 1.8, I think it's 1.78 or something like that. I could be wrong. Anyway. So different, the point is you can get different optical behavior by choosing a different ceramic material. Okay, so it's a property, it's a useful property. Reflectance, you get different amount of light reflected off the surface of various classes of ceramics. Particularly at an incidence angle of 0 degrees, so normal incidence, perpendicular to the surface. The reflectance is n minus 1 over n plus 1 squared.
What's the significance of reflectance?
So the amount of light that's reflected off the surface of water is different than the fraction of the light that's reflected off the surface of water, for instance.
So that's like a fraction of the intensity?
Right, so reflectance, right, it's the power reflected versus the power incident, the ratio of the power incident.
Kind of, it tells you how much energy can be absorbed in the light, right?
It's how much energy is reflected as opposed to.
Well, I mean, but if you know what your incident energy is, then the leftover is how much would have to be absorbed. It's not enough to be absorbed.
No, it should be transmitted too.
Okay.
Right, that's how windows work. Okay. So for instance, for window glass, what's the index of refraction approximately? 1.5, right? We're probably using 1.5. So we have 3 halves minus 1 over 3 halves plus 1 squared. So that's going to be 1/2 over 5 halves squared, which is 1/5 squared, which is 1/25, which is 0.04 or 4%. So roughly speaking, 4% of the light that hits a glass window is reflected back. Right? So if there's, I can see myself, I can see my reflection in the mirror, in the window. I can see it very prominently if everything on the other side is black. Right, because then there's no light coming from over there, so the only thing I see coming off the window is my own reflection. Make sense? Yeah.
This is like an angle.
Yeah, this is just at the window increase, at normal incidence.
That's how two-way mirrors work, or one-way mirrors work.
That's how, yeah, that's how it's not coded anyway. That's how a one-way mirror would work.
Wait, you put coating on it? That's only gonna work.
You can put coating on it that enhances the amount of reflection.
But still, if the backside seems clear.
Right, so you put a thin layer of aluminum, so it's not enough to fully reflect. So if I use diamond, right, just for kicks, let's say that that's 5 halves. Right, 2.5, it's not quite, it's close. So that's going to be 3 halves divided by 7 halves, which is going to be 3/7 squared, which is 9 over 49, which is approximately 18%. So 18% of the light is reflected off a diamond. So diamonds are sparkly. Right? Because a lot more of the light that shines on them is reflected. There's other issues we'll talk about later too if I have time. There's 2 kinds of reflection. Off angle. Specular reflection is this. Specular reflection is theta I equals theta R. Right? The angle of incidence of light coming in, hitting the floor, being reflected. So specular reflection is the image, the mirror image of the lights in the room that you can see in the floor. That's specular reflection. Diffuse reflection, on the other hand, is scattered in all kinds of directions. So if I have a surface like this, if I have specular reflection, it's going to like that. The light's going to come in and go off, come in and go out like that. That's specular. If I have diffuse, it's completely diffuse. The light comes in like that, and then is scattered, where the length of each of these vectors corresponds to the relative intensity. Like that. That's diffuse. Okay, scattered in all directions. So a frosted window, right? I'm the one who's allowed to sing in class, not you. A frosted window has a diffuse surface. They basically, you grit blast, you sandblast the front surface of the window, makes it rough, light comes in and scatters equally in all directions. It's a diffuse reflector. A clear window, not so much. And you can get diffuse reflection from the surface perturbations. You can get it from, you were talking about why is Corningware white, right? That's diffuse. Right? The individual components are actually clear, but the whiteness comes from the fact that you get this diffuse scattering. And if it's fully diffuse, then light coming in from this direction scatters equally in all directions. That looks white because all the light coming from all the room comes off to my eye. Does that kind of make sense?
So, can you see your reflection in the window less well if you polish the window? You can see less than 4%?
No, that's an inherent, the 4% is inherent in the, that's the specular reflection. This is all specular. So if I have a specular surface, right, hitting normally incident, as I go to a higher and higher angle, I get more and more of it reflected. It's a larger than 4%. Right. The smallest amount I get is when I'm straight on 4%.
So polishing the surface has no effect on that?
Right. Unpolishing the surface, roughening the surface, right, will cause that light to be reflected. If you look at it in a microfaceted way, some facets are going to be angled at another angle, some are going to be straight down. This is for specular reflection. Okay. Any other questions about the reflection? Okay. Next, reflectance, next would be transparency. So this is kind of like the diffuse reflection, but now not due to the surface, instead due to subsurface. So, three different degrees of transparency. One is transparent. You can see light completely through it, that's what the glass is. Glass is transparent. Second is translucent. That means it doesn't absorb anything. Perfect translucence doesn't absorb light. It just scatters it. So that if I have a piece of glass with a bunch of titania in it, titania is actually a transparent medium. You can see through titanium. If I had a uniform film of titania, it would be clear. But the titanium powder, like I said, has a weird refractive index thing that causes the light to scatter around. So translucency basically means all the light's going through, but it's just not going through in a straight line. It's being scattered into diffuse directions. Okay. And that could be either a second phase caused by a second phase. In other words, the intersections between grain boundaries, between grains, where the light is basically just refracting many times as it goes through grain to grain to grain to grain to grain to grain. And that multiple refraction ends up looking like scattering on a macroscopic scale. Or it can also be caused by pores. So if I have a porous piece of glass, it will look translucent because of little pockets of air inside there.
And that's because it has a different index of
Because the air has a different index, dramatically different index of refraction. So it would take less porosity in an equally thick piece of glass than it would second phase materials in order to cause that scattering. Yes?
Does changing the direction of light require energy?
Changing? No, it does not.
Because of the mass?
Because they have no mass. And the photons have no mass. So it does not, it's not a, what's that?
Maybe have momentum, so would it take?
Yeah, but it doesn't take energy to change the momentum. You know, the momentum is still conserved, or the energy is still conserved in the process of the photon. So I can answer no. So it doesn't, you know, to redirect a light. Okay, 2 minutes. All right. Sorry, talking too much. And the third category then is opacity. And that is where it absorbs the light. You get no light through. So opacity can be because all the light was scattered back out the front and nothing made it through. So in the Corningware example, I shine a laser on the Corningware. If no laser, you know, no light goes through, it's because all the laser light is scattered out the front side. Okay. Or it could be by absorption. So if I put little bits of metal, even if it's just atoms of metal, they can absorb energy.
So opacity means 100% reflection because it's all coming back.
Or absorption. That means 0% transmission.
Okay.
It could be a combination of reflection or absorption, right, Well, theoretically?
Right. Right. But the reflection would typically be scattered reflection.
Yeah.
You get 0% transmitted. The last category then is color. So color derives from wavelength-dependent absorption. So if I put some chromium ions, if I dope my aluminum oxide with some chromium ions, those chromium ions will absorb yellow light. They'll preferentially absorb yellow light. so that when I shine white light on something that's been, aluminum that's been doped with chromium ions, I think that's correct. I may be wrong with that. Chromium might be absorbing green. I can't remember which one it is. It's nuts. I should have written it. Oh, whoa, 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 whoa. I might have it. Chromium. No, okay, okay. Chromium absorbs, yes, it doesn't. It absorbs blue-green light. Chromium absorbs blue-green light. So I shine light on aluminum oxide that's been doped with chromium. It absorbs the blue-green light out. What gets transmitted? If I take away the blue-green, what's left? Red. And so I call it a ruby. Right, so a ruby is just aluminum oxide doped with chromium. Sapphire is aluminum oxide doped with either titanium or iron, which absorb the yellow or red and make it look blue. Emerald is a more complicated ceramic, but it's doped with chromium as well to make it look green in that context. Amethyst is silicon dioxide with iron or manganese to make it look purple. Anyway, just going through several of the gemstones. Gemstones are ceramic, are crystalline ceramics.
So why is it so, why is that invaluable? Is it hard to make that?
So, yeah, so the thing that makes them valuable is the fact that to make them, they're a single crystal, right? Each gemstone is a single crystal. And so, you know, the largest diamond is the largest diamond because it's the largest single crystal.
Yeah, I should go.
The stuff you get.
I'll do that.